So I don't want to give you the idea that everything is strange and different. It's just that I wanted to have some examples. I feel like whenever I do pure mathematics, I need to have an example in my mind that stretches it and gets me to the right place I need to go. So for example, if you think about, the real numbers fits for almost anything that you can think of. It's a Banach space. So in real analysis, it's an example of something. It is also a field. So you can think of the real numbers works for everything. So it's a pretty useless example in some ways. It doesn't push my mind to think about what particularly is important to the real numbers, what makes it unique. Sure, it's a group, it's a field, it's whatever it is, but it's not enough of a unique example that gets me to understand the theory better. So it's almost like the examples are what's driving the theory or making you understand the theory. So if you have some examples in your head like the braids now, you can ask yourself, well, here's something that I have to prove. Is it true for those braids? I know it's true for R, everything's true for R, right? Is it true for those braids? Would this be true for the complex numbers on the unit circle? You can start thinking of these weird examples or these non-standard examples as ways to test the conjecture out and understand why it's working. And that's where I think the problem is of using always integers or even the modulo integers. So z with plus, it's a binary operation. I hope so, because I've been telling my little kids that for some time. If you add two numbers together, you get another integer. In fact, multiplication is also a binary operation on z. It's a binary operation, sure. I take two integers and multiply them, I get another integer. And so on, right? What about matrices? If I take two matrices and add them, will they end up being a complex number? No. If it's doable, is that multiplication going to be a binary operation? If I can take two matrices and multiply them, will they always give you will that give you a binary operation? Well, the problem is A can't be paired with every B, so you have to kind of whittle down and make sure that this makes sense. But then you get a restriction. So what if I, for example, work with just square matrices? What if I took two square matrices and multiplied them? Will I still get a square n by n matrix? Yep, right? So that kind of makes it so everything kind of stays in the same place. So, and we call that set M2 of R. I checked in his book, he has something like some notation like that. So yes, multiplication on n by n matrices is a binary operation. What about the dot product of two vectors in Rn? If I take a vector with n components and dot product it with another vector of n components, is that a binary operation? Why wouldn't it be? Alex?
It gives you an integer or a number.
A scalar, right? So, right. So if you're working on Rn and n is greater than 1 and you dot product with another vector that's in Rn, the problem is that you get something in R1. So you don't get something back in the same set. So it is a way to pair two vectors, but it doesn't get you back into the same set. So the dot product is not a binary operation. So again, as we go through the semester, I'll have examples where something is, interesting examples where something satisfies the definition. By interesting, I mean not R. And then I also will have something that's not. So I have a good idea in my mind with examples of what a definition is. I thoroughly have a picture in my mind of what those examples are and what that definition means. This is going to be our last example today, and then what I'll do is I'll go back, if you want to take notes on any section, I'll go back and have you take notes on those sections. How many of you use Galleon for your undergrad textbook? It's actually a great book. You use Galleon? It's a great book. Do you have me? Okay. Good. Well, maybe not good. If you do really well in here, I'd say, well, I wish it was me. So if you take a regular polygon, you rotate it, you can swivel it around. And I rotate it to the point that I make the same shape back. So that animation there was rotating it enough till I get it to click back into the same shape I originally had. But it's not in the same position anymore, because I took it and I rotated around until I got the same shape again. That actual rotation is a movement of that original polygon. And I could also reflect that polygon. I could take the polygon and flip it over the line, like that. If I did that, the act of rotating first and then flipping is a binary operation because I'm working on the regular polygon and I get the same regular polygon back. So I'm still working on this same set. But I'm pairing the set by actually acting on it 2 times, right? So if I label the vertices, then you can see that it's not actually, because when it was all blue, it's hard to see that you're getting something different. So if I rotate once, that's what I get, right? Clockwise, I get that shape. And then if I flip, I get this shape. So this is an example of something called, where we're going to look at something called the dihedral groups. So those are really interesting examples because I think that's really where abstract algebra is made for it. I had once thought about teaching abstract algebra from this book called Abstract Algebra Using the Rubik's Cube. And that would be a totally different way to think about it. Right? You're actually moving on the Rubik's Cube and you're turning and rotating and flipping. So it's the whole idea of the geometry that you're moving around. And that's more where I've seen abstract algebra used. There's a chemistry professor who always loves when I'm teaching graduate abstract, and he talks about the symmetry of shapes, or symmetry groups we had last semester from PDEs. So the symmetry that you're looking at, the symmetry groups, are also something to do with abstract algebra. So I'm going to leave you with a question because I should always leave you with something to think about, right? So if you took the shape that you just saw and instead of rotating first like I did and then flipping, would you get the same answer if you flip first and then rotated? And that's along the lines of your question with the braid groups. You're asking about commutativity, which is more than but just binary operations. Another question that you're asking. So you can answer that one for the braid groups too. So that's something to answer for next Monday. And we're supposed to have quizzes Monday. Next Monday we won't have a quiz. We'll have an in-class assignment. We'll have an in-class assignment Wednesday as well. And then the following Monday we'll start having quizzes.